Okay, now Hooke's law is a way to understand springs. So let's say we have a spring, and the easiest way to visualize it is imagine a spring hanging from a ceiling, and there's nothing attached to that spring. Okay, then that spring has a certain length to it that we call the rest length, meaning that the end of this spring, the edge of this spring that's freely hanging, is located at a position 0, which we refer to as equilibrium. Now, if I were to hang a box or some mass to this spring, it's going to stretch the spring out some distance. Okay, we're going to call it delta x or change in x, but it's referencing the distance the spring has stretched from equilibrium. Okay, so now to understand what the spring is doing, let's look at the forces. So if I make a free body diagram, there are two forces, right? Gravity is easy, but if that box comes to rest at that low point, that means gravity's trying to pull it down and there must be something pulling it up. Well, what's attached to it? The only thing trying to pull it up is the spring. So we're going to define that as a spring force. And that spring force is trying to fight against gravity. Okay? Now Hooke's law tells us that this spring force is equal to negative k delta x. Now what is delta x? That is our distance from equilibrium, and k is what we refer to as a spring constant. Okay? It is a property of the spring. So if you think about it, imagine like a rubber band, right? If you take a rubber band, there's many different kinds of rubber bands. Some that stretch a lot, some that stretch a little. Well, the harder they are to stretch, the greater the spring constant they have, right? Think of a slinky. You can grab a slinky and stretch it out pretty easily. But then if I give you a shock absorber in a car and ask you to stretch that one out, you're going to find that it's a lot more difficult. So that all comes down to the spring constant. Okay? And sometimes in some problems you'll see it referred to as the spring stiffness constant. Okay, and the units of the spring constant come out to newtons per meter. Okay, and when you're talking about how much a spring can stretch, that should make sense. It would cost how many newtons to stretch it a certain amount of meters, right? In this case, for the unit, it's 1 newton required to stretch it 1 meter. Okay. And then the negative sign, because the negative sign tends to throw students off. Well, the negative sign will make sense. The negative sign refers to the fact that this spring force is a restoring force. Okay, and by restoring, we mean it's always trying to return to equilibrium. Okay, so if you think about it, the box is being pulled downward by gravity, right? So the displacement from equilibrium, delta x, is actually a negative number. It's going down. So if I do negative k times a negative number, the overall spring force is positive, upwards, right? If I were to take that box and put my hand under the box and push it up past equilibrium, then the spring is trying to push down to get back to equilibrium, right? So an upward displacement, positive, times a negative k, means a negative spring force. So the negative is put there so that no matter which way it moves, the spring force is always trying to return the box back to equilibrium. Okay, and so that expression, spring force is negative k delta x, is what we refer to as Hooke's law. Okay, now when you think about it, gravity pulling the box down, maybe it was a box on a horizontal surface and I pushed the box in. Either way, Hooke's law applies. All right, so let's do a quick example. Let's say we have a 5 kilogram object and we attach this object to a vertical spring. Okay, and doing so causes the spring to stretch 8 centimeters. Okay, and at this point we allow the box to come to rest. Now, how far will the spring stretch if this object is replaced with a 12 kilogram box? All right, so let's do a picture and visualize it. So first we have a 5 kilogram box which stretches the spring 8 centimeters from equilibrium. Okay. Then we attach a 12 kilogram box and it stretches the spring further. And we need to know, well, we want to know how far from equilibrium did the 12 kilogram box stretch the spring. Now, before we can solve the problem, we have to know what is the spring constant of the box. Right? In order to get the spring constant, we're going to use the information we were given in the 5 kilogram box scenario. Right? If we look at forces, we have the spring force up and gravity down. So it's spring force minus gravity, and the spring force was minus kx, which was Hooke's law, minus mg. And we need to solve this for k. So the displacement was negative 0.08 meters from equilibrium. And so when we separate this out, the negatives are going to cancel. And we get 5 kilograms times 9.8 divided by 0.08 meters, which gives us a total of 613 newtons per meter for our spring constant. So now we can go to the 12 kilogram box. Okay, because even though we put more mass on the spring, we haven't changed the spring, so it still has the same stiffness. So same free body diagram, spring force up, gravity down. Spring force is minus kx, gravity is mg. Now we're solving it for delta x, so that's 12 kilograms times 9.8 divided by our spring constant, which we just found is 613. Okay. And when we crunch that out, we get negative 0.19 meters, which means that it displaced 19 centimeters below equilibrium. All right, so now we're going to look at the work done by a spring. Okay, so let's do an example like we did in our previous problem. We have a box hanging from the ceiling, okay, and it's hanging from a spring, and it stretches the spring some distance, we'll call change in x 0, from equilibrium. Okay, now sometime later, after releasing the box, okay, while it's moving upwards, it's moved to a new position as it's going towards equilibrium. Okay, so if the spring is what's making it move, then the spring is doing work. So we want to calculate how much work is being done by the spring. So it's a force over a displacement, and in this case we know the force, right? It's a spring force, and we know the limits go from these points, change in x of 0, change in x1. Force was spring, so minus kx over delta of change in x. So now we need to calculate an integral. So k is a constant, so we'll pull that out. And now we got to do the integral of change in x0, change in x1 of x dx. Okay, so hopefully that's not too difficult. We're going to add 1 to the exponent, then divide by that number, but we still have to evaluate between the limits. Okay, so we got minus 1/2 k, change in x1 squared, minus the negative 1/2 k, change in x0 squared. Oops, that square should have been on the x, not outside the parentheses. Which will be minus 1/2 k, change in x1 squared, plus 1/2 k, change in x0 squared. So then what you see is an expression to calculate the work done by a spring in stretching it or compressing it from an initial position x0 to a new position x1, all measured from equilibrium.